The assignment given to us was to search for an object that we could record moving at a constant velocity, record it, and then upload the video to Tracker to plot the position versus time data of when the object was at constant velocity. At the same time, we had to create a program that showed the theoretical way the ball would move at constant velocity by using Newton's second law. Then create a final graph comparing the theoretical and experimental data and see how well the theoretical data reflected the actual movement of our object. The object I chose was a small ball that my dogs play with, and I recorded it rolling on a 1.5 meter long table. This is the video. As seen, the data plotted only reflects one small clip of the video. The reason behind this is because when the ball is pushed and when it falls off the table, there is a force being exerted on it which affects the velocity. In the middle of it, during that small clip, no force is being exerted on it, and therefore, through Newton's second law, we know that the velocity is constant. The graph that comes out of this video shows an almost completely straight line, which means that the velocity was very constant. To find the velocity from this graph, because it is position versus time, is just to find the slope of it. For the theoretical part of it, the program I created used the mass of the ball, which was 0.1 kilograms, the velocity of the ball, which we got from the first two data points of our graph, and the initial position, which we also got from when the time was equal to 0. The delta t that I chose was of 0.01 seconds, and the moment when the video stops taking the data is at 1.068 seconds. Then, using Newton's second law, which is this, which just says the final velocity of the ball is equal to the initial velocity plus the net force divided by the mass plus times delta t, this loop would update the velocity of the ball at every moment, as every 0.01 second passed by. The net force for the velocity to be constant has to be 0, and that is why this is set to 0. Finally, if we run the program, we are able to observe how this small dot represents the ball and how it moves from right to left, just like the video, and then we can see the graph that comes out of it, which is very similar to the experimental graph. After putting both of these data together, we are able to see how both of them are very similar, and they come together very well, meaning that the theoretical data reflected our experimental data very accurately. To understand why the slope of these graphs is negative, we must go back to the video. In the video, I chose to have my origin at the spot where the ball started. That means that the y-axis is the vertical one and the x-axis is the horizontal one. If you move from the origin to the right, your position is going to be positive, and if you move from the origin to the left, the position is going to be negative. Therefore, because the ball is moving from right to left, it has a constant velocity, but it's moving in a negative direction. From the video, if you watch it completely, you can tell what the push was and what made the ball stop its constant velocity. But if we go back to the theoretical model, there's only a movement in a constant velocity, and the position moves in a linear form. But there is no way of knowing what the push and pull were to make the ball go in that velocity. The conclusion of this experiment is that the theoretical calculation was very close to the experimental calculation, proving that Newton's second law actually does apply to an object that's going at a constant velocity.